I'll give the quiz back, I think, in the next class, because it's going to take me a while to distribute it. You probably know the answers to the stuff. I was kind of surprised that over I think like 11 of you got the answers right. 3 of you got it completely wrong. Most of you wrote false and true, right? Was that because you didn't read the textbook or because it was not clear? Kind of curious that everybody came up with the true for the second one. Yeah.
But the last, I think after the fact that your true and false was referring to the entire paragraph, whether the entire paragraph was true or false. And now sort of focusing on the last question about something about the kernels, and I was thinking, I didn't talk that much about the about the kernel affecting the medium term or the long term or short term. So I think if I focus on the whole question better, it would make sense.
Okay.
Agreed. Agreed.
So you thought part of the questions was right, part of it was okay. So for the midterm and for the assignment for the in-class exams, I would like to give like true or false kind of questions, right? So the most part, I'll try to be more clearer, but try to read the whole question and make hopefully that'll be clear, right? So you think if you had read it like a couple more times, would it?
Well, mostly I thought that your sentences at the beginning were statements of fact, and that you're only asking about the last part. So that was the part that confused me.
So as part of the true or false, I probably state a lot of facts, and some of them have no consequence to what the answer is, right? Because otherwise, true or false becomes so trivial, right? So, I think I was trying to throw in facts which have no consequence, and some things which are blatantly wrong, which look like facts, right? So I'll try to make it more clearer for the exam, but it'll be more of this kind of stuff. And so be aware that your exams would have a lot of facts that have nothing to do with what is being asked, and since it's true or false, true or false are multiple choices. Right? Like, yeah.
The true or false part is just about the last sentence, right?
Yeah.
Okay.
Yeah, whatever was asked, right? Yeah, so I'm not asking whether the whole sentence is true. I'm just asking whatever I asked, right? And if it's not clear, at least in the exams, you get to. Exams I would like to give like 6 questions, and you have like half an hour. So if it's not clear, write down what your interpretation was, and that really helps, right? And in this case, we can just do that. So, are there any questions so far about processes and what have you, right? So one of the hardest part with the OS is there's a whole bunch of stuff that we haven't covered yet, and it kind of depends on the stuff, right? So somebody was asking me, like, how this memory organized in a real machine, right? So when you talk about real machines, you have notions of virtual memory and physical memory, which we won't get to it for quite a bit. This is in the 3rd module, right? So for now, assume that the memory is like this big square we talked about, and not figure out where it's being placed, right? There's a notion of how do you read from the program to fill up on the structure, and that would need understanding file systems and files and all those things, which we'll get to later, right? So for now, magically from your CD or disk, the program gets loaded and it starts running, right? But as we add more stuff, things will become more clearer, right? So in the last class, we were talking about process concept, and the notion, process is the way that your operating system kernel knows about a program which is executing, right? It keeps track of all the stuff about the process, what's the state it is, and what are the resources which are allocated to it, hard disk or what have you, and what are the states of each of those, right? And as we progress, we'll see what that means, right? For example, for hard disk, it needs to keep track of what it was reading last or something like that, right? And from each program's perspective, they get the whole machine. They don't really know that others exist. They don't know that they are being context switched, right? We look at what happens for a context switch. But from a program perspective, they don't know that they're being context switched, right? The context switch has to be such a way that you get interrupted, the OS stores all the state, and then puts somebody else and then keeps running. So the only way for you to figure out that you're not getting enough CPU is by timing, right? And that's probably what you are learning from your homework project 1. So how many of you? So I haven't gotten the group member list for all of you, right? So I'll probably send an email to the people who haven't sent me an email. So does everyone have a group member, project group member?
I don't have one.
You're the only one?
I guess so.
Okay, so one group asked me. I mean, they were 3, and they want to know if they can stay as 3, right? And they can't. I mean, they have to. Yes.
I sent you an email just a little while ago.
Oh, just
Because you said there might need to be 2 groups of 3.
Yeah.
So, I mean, I can be right here.
Okay. Okay. Yeah.
With all due respect, like, it's a great idea, but I mean, the amount of emails getting sent back and forth on that listserv is kind of ridiculous. Like, just like, would it be possible to just set up like a little forum on the class website or something, where people could post there instead of?
That's fine with me.
Just email it to.
It's either is fine with me, but some people like emails, some people like forums. Yeah.
Like when I emailed you, I just emailed you instead of the entire class.
Yeah.
Or my group or whatever.
So
that'd be helpful. If people just emailed you.
So there are 2 things, right? Like the way that OIT sets up the mailing list, only I can send to it, right? And everything has to come to me, and I approve it, and then it goes back to you, kind of stuff, right? I find it kind of annoying because that depends on me being around. So the other way I can relax it is to say you have to approve any message you send to the mailing list, right? And usually people tend to forget that once you send a mail to the class, you have to wait for the listserv to get something back, then you have to approve it, right? So right now I configured it, whereas you send a mail to the class mailing list, it goes to everyone, right? So the one way is to make sure that the mail comes to me or the class, or to make me editor or make you the editor to see which should go there, right? I've had people who don't like the online forums because then there's some page you have to go to check what's being discussed, right? You can also set up your listserv to send you mail once a day, collect everything, send you mail once a day. And would that solve the problem?
Yeah, sure, that's fine.
I mean, I would like to set up a mail forum, but if there's enough consensus to set up sort of a discussion forum, they'll be fine. But then you need to like register for something, or I don't want to use Vista because I don't like the fact that Vista is all you have to log in and it's not public and stuff, right? So let's try that one, and in the future when you send an email to the class, be aware if you send it to the class, it goes to all of you and without any editing. And if it gets a real problem, then you can try to say something. Right? So, okay, so that's where we stop, right? So one of the things that happened so far is that processors are by themselves. Sorry, I forgot. So how many of you finished your homework project 1? I know some groups have finished it, right? So some of you have finished the project, right? So now I don't want to point out who they are, but if you have finished it, then you would understand what I was saying. If you haven't finished it, try to get on the project soon, because one of the things you'll find out, the reason why I left the mailing list open like that is when you start to work on this stuff, when you start to do the kernel, right? My instructions do not say exactly precisely what you have to do, right? Because I think that defeats the process. If I said go to the machine, sit down, log in, go download the stuff, and if I say exactly everything, then you don't look around, and my idea was for you to look around, right? So when you start doing stuff, bad things happen, right? Some machines crash and for weird reasons or what have you, right? things don't go precisely the way you expect them in the precise order that you want, right? So it's better to start early and look at the stuff, right? And when you have some problems, I want you to send a mail to the class so people can respond to you in fairly good order. So that's why I don't want to be there, because then that means that I need to be online all the time to approve each message, right? So people from outside cannot send message. Only people in the class can send mail. So hopefully we won't abuse that, right? So you will see that if you change the Hertz value for your homework project, your programs learn slower or faster, right? But from within your program, you can't really tell what's happening. From within your program runs to completion, it does what it has to do, except one of them learns slower and one of them learns faster, right? For the most part, they don't talk to each other, and that's fine for some applications. That's fine for applications because it protects you from the effects of the rest of the system. But it's not fine when you want to collaborate, when you want to do stuff with other programs, right? Because you want other. So, for example, if you're building your PowerPoint and to use a spell checker, right? It has to figure out how to talk to the spell checker so they can communicate, and you can have one spell checker for the machine where these things communicate, right? And and that's the cooperating process. They're trying to cooperate with each other. They want to be able to communicate with each other in the same machine. And there are two different ways of doing that. One is using a shared memory, other is using a message passing. And as we'll as we progress, we'll see how you'll implement many of these stuff, right? But the idea with the shared memory is the kernel makes some part of memory common to both the processes, right? You have to somehow set this up. You have to tell the kernel that I want some part to be shared. For example, on the A graph, right? The memory M becomes shared, right? Which means that the OS gets involved. It says that these two can share this M. It's not a violation if they write into the same thing, right? And anything written by one process is immediately seen by the other process, and vice versa, right? And again, it has to involve in the kernel, because kernel's job is to protect you from the bad person. So it has to know that this is happening, right? And as we'll see, this also involves that when it's getting rid of process B, it has to be aware that it's being shared with other processes, right? So for now, the assumption is, somehow the kernel makes this possible, so anything you write here, the other things can read it, right? The next module is basically trying to figure out how to make this happen nicely, right? And I'll tell you what that nicely means. We'll see a little hint towards the end of the class, right? The basic idea is if there are two of them doing some things, they have to coordinate with each other, or else there could be chaotic stuff, right? If one of them writes something, another one also writes something, you have to be clear which ones survive and stuff like that, right? The notion of the message passing is this other way of communicating, right? And message passing is similar to your first-class mail notion, right? You create a message, you send it to somebody, right? And you receive messages from somebody, and that's how you process. If you want to talk to another process, you create a message, send it to the other process, and the other process acts on it. And when it's done, it sends a message back to you, right? And doing this means that there is no way to simultaneously make any modification, right? Because only one of you has the envelope. So if I send the message, right, the other person has to wait till they receive it, and then they get the message back, right? So there are some advantages in using both approaches. Shared memory, you don't know anything. It just looks like so if you conceptually, it's similar to saying, this need not be a semantics, but essentially I'm saying I want a shared allocation to pointer, right? And from then on, I should be able to do something like this, and both of them should see it, right? If the shared memory was set up right, this should be fine, right? If I were to use a message passing, I have to say send 1, right? So I send the value 1 to the other process receives it and then does something, right? So what is missing with the send, the conceptual stuff? What else do you need for send to work, right? As I send the value, it's missing one thing more fundamental. Yeah?
Where it's going to?
Yeah, so you need the way to,
the address, right? And that lies the complication, right? You have to have a way to name stuff, right? So processors now have to have names. I need to figure out what the name is to send the message, right? So if I have a machine which is running PowerPoint and Word, right, and if the Word has to send something to PowerPoint, it has to know what to call PowerPoint, right? And so the OS has to give it a name which is useful, right? So if the OS gives a name of pen or some random number, right? Random number like the process ID, that's no use, right? You can't say I want to talk to process 10. You have to say I want to talk to PowerPoint, right? Which means that these applications have a name, the OS has to manage the name, and they have to communicate with each other, right? And we'll see later on how these things affect. And essentially, that's what happens for microkernel systems, like your Mac, right? Which is the Mac OS X, right? Essentially, they communicate with each other using messages and ports which are very much like your email mailbox, right? You create a port, you send something, and you have to know the name either by yourself or you have to ask somebody to know what the name is. You have to ask who's right now listening for PowerPoint, right? And you have to register and all those things, right? So there are a little complication, but essentially the idea here is once you know who it is, you just send the message over and they receive the message. To give you a sense of how the shared memory stuff work, we'll go through a little code segment for a producer-consumer, which is a classical problem that most of the systems would talk about, right? So the idea here is there are two programs. One of them is producing content. The other one is consuming content. So if somebody keeps adding some stuff, somebody takes away some stuff, right? So let's call this shared stuff buffer, right? And there could be a whole bunch of stuff here, right? These buffers are bounded. I mean, nothing is infinite, right? So the buffer has some size, right? So if the producer puts some value here, right? Let's say it fills something, right? And the consumer can use that, right? For example, the producer can produce a number, the consumer may print it, right? So the producer keeps producing fast, right? Consumer can eventually come up and using them. If the producer tries to produce more than this, it has to be stopped, right? Because it can only go up to a certain point, right? And that's a producer-consumer problem. And we'll revisit this in terms of how to do this waiting and letting it go, right? We don't know that yet, so for now it's just the notion of how they proceed, right? So here the example is your buffer size is 10. So you create a buffer of size 10, and you have two variables in and out, right? Essentially these pointers, right? Where you're trying to add more items and where you're trying to get these items away. Yeah.
Could you create a buffer of dynamic size that can grow or shrink if you needed to?
You could, but you need to keep track of what the current size is in software, right? And in this case, we're not doing that. There are a lot of reasons why you don't want this to keep changing for simplicity purposes. Right?
Okay.
Yeah, but you could. I mean, you could, like when it comes here, make the size grow bigger and so on, right? But for the most part, when you talk about producer-consumer problem, you're talking about producer producing something that should be consumed by the consumer, right? If this has to be increased beyond limit, that means the consumer is not fast enough, right? So in the abstract example, there's something wrong, right? So if I'm talking about a printer that I'm producing, right? If I'm producing something at 1,000 items per second, and you can only produce one at a second, right? You have some problem. You can't keep that forever. I mean, you can keep increasing the size, but eventually you run out of space, right? So that's the stuff we're talking about. Yeah.
So it's a problem if the producer is producing so much that the consumer is too slow?
Yes.
Is it also a problem if the consumer has to wait too long for the producer?
Yeah, but usually so if the consumer has to wait, right, there is no problem with the buffering itself. The consumer just is sitting around doing nothing, right? But the buffer won't get filled, so whatever size you have should be fine, right? So it's not considered a problem because the consumer just sleeps, right? Yes?
I was wondering, once this buffer has been created by the operating system, will it manage it, like if you try walking off the end of the buffer and storing other data points?
So the creation of the buffer has something to do with the operating system, right? This is the generic problem of producer-consumer, right? The OS does not create or manage it, right? The OS can only make it shared between two processes, right?
Okay.
So if you go off the end because your program has a bug, whether it fails or not depends on stuff that we'll see later, right? So if you have way to protect anything written beyond that, you will fail, right? And that's in the memory management section. But for the most part, you may or may not fail depending on how things go, right? If you want it to be fully protected, then your program will be slow because you're set up out of protection domains, right? But we'll see we'll come to that later. But usually, the OS does not promise anything. Operating system does not know that you're doing this, right? All it knows is you ask for a buffer, and this is one classical way of using buffers, shared buffers to do stuff, right? The kernel does not know what you're doing with it, right? Does that make sense? So these are we'll see a lot of these example scenarios, right? Which make a point, right? In terms of what OS is doing all over the place, right? So these are abstract. Real implementations may increase the size, what have you. But in general, you don't increase that because we're talking about a producer-consumer problem, right? You want these things to be kind of matched where producer and consumer should be able to live with some finite size, right? So think of this as your net. This is what you do for your printers, and you do for your keyboard, you do for your mouse, you do for your most of your input-output, right? Your network drive and stuff, right? If you're typing too fast for your CPU to manage it, then you have a problem, right? So this should be in the handout. So essentially, you have the producer and consumer, right? And for this moment, just assume that they're both running parallel somehow, right? They're running in two different applications, right? So the producer would add something, do that little math up there, right? In +1 bus size. Essentially, this keeps rolling around, right? And it keeps track of how much is produced, right? So this is the maximum it has produced, and the out pointer tells it how much has been consumed, right? And you can only store buffer -1 items because that's the way it kind of keeps going, right? So as you produce more stuff, the in would have been here, right? And as you consume these things, the out keeps moving up, right? So essentially use that to figure out how many items are in the buffer. And if there are no free buffers, the third sentence says do nothing, right? And that's essentially at this point you can't do anything. So if you have some of the more elegant solutions we look at later on, you would wait. Otherwise, you do what is called a busy loop, right? You just go in a tight loop doing this stuff, right? So essentially, this is a way for two entities to cooperate with each other to dump some information that the other one consumes, right? And the buffer size depends on how much you expect it to be outstanding, right? And you have similar problem with the message passing stuff too, right? When I say send something, right? If I keep sending it to you and you don't receive it, it has to be held somewhere, right? You have to have buffer for it. And eventually the buffer has to fill up, right? Think of this as your mailbox, right? If I send you 1 mail a day, your mailbox can probably hold, right? If I send you 1 million messages, envelopes a day, right? Unless your post office gives you a separate bag for it, right? Something has got to go. Something has either somebody has to tell me that stop, or somebody has to start to throw messages, right? You can't keep up with the stuff, right? So depending on how you manage these things, you can either make me stop, right, or you throw away most of the messages, right, and to deal with the stuff. Even here, there's a finite amount of stuff you can withdraw, right? The assumption here is you are able to deal with the amount that I can send you. So if I send you one in terms of mail message, it's similar to a mail message, right? If I send you one email, you can probably deal with it, right? But if I suddenly go crazy and every second I send a mail to class, right? Eventually, at some point, somebody has to tell me back off, or you start deleting messages without reading it, right? Or your quota runs out and OIT does that for you. Right? So that's the notion of processes. So we kind of know this is the mechanism for you to associate and run a program and what have you. And the next concept we have to look at is the notion of threads. And I think she brought it up in a prior lecture on how to do things in parallel, right? So far, with the process model we looked at, you have one CPU assigned to you, and the one CPU can do one thing, right? And if it wants to do something else, it has to talk to another process. Using the sharing mechanisms, you can talk to another process, right? But most modern machines that you would buy these days have dual core or more, right? Which means that you have 2 CPUs, right? So you can use 2 CPUs to run 2 different programs, but there is no way to run 2 CPUs to a single program, right? So the notion of threads give you that facility, right? So far what we assume is we have one thread, one thing happening within your program. So when you think of that stack and heap and so on and so forth, and you have I think this is what the graph had, right? You assume that you're running functions within this one stuff using like one thing, right? And that's called the single thread, right? So the notion of threads says that you can add more CPUs by creating multiple threads of execution, right? So you still retain everything else, but now you have multiple threads doing different functions. If you have 2 or 3 different functions on the same program, they can all be doing different stuff, right? And since they're within the same process, so they are kind of subset of, they're inside the process, right? So right now the process says it has access to some other IO stuff, disk or what have you, and how many CPUs you have, right? So the more CPUs you have, the more faster you can work, right? But they also share everything. So all the stuff, all of the threads have access to all this content, right? So figuratively, this is how it looks. So if you over the left, the single-threaded process is what we talked about so far. The notion of threads means that you can create multiple, you can assign multiple CPUs, right? Each of the CPUs needs its own registers and stack, right? Because each of the functions would be running their own stuff. And as we saw in the last class, stack is the one which tells you where to return. So each thread has to know where it's going and where it's returning, right? But the global variables are all shared by all of them, right? The idea here is, I'll show you an example of what threads are and how you use them a little later, right? The idea here is, if I give you more processors, then you can do stuff better. You can be more responsive, right? So if you have a dual core machine and you have 2 processors, you can have one of them sitting in the background always doing a spell check while you're typing, right? You can do the reformatting and all as you're typing these stuff. So your system can actually perform better, right? In fact, I think Intel wants to go to 40 or 80 cores sometime soon, right? So once you have lots of these things, they're sitting there and they can do their own stuff, right? There is another multi-core machine which is sort of almost popular. How many of you have PSP3? The PS3, sorry, the Sony PS3.
My roommate does, so
okay. So do you know much about the processor inside the PS3?
No, not really.
So
That's pretty sweet.
yeah, so it's very sweet. I think it's awesome. I think it's really awesome, right? So it's a 14-core processor, right? It has a 14-core plus a main control processor, right? The main control processor is a Power PC, and there are 14 cores which can do stuff, right? So since they cannot guarantee that all the 14 can be built to perfection, they only give you, I think, 7, right? The other 7 are for if one of them fails, so they don't have to manufacture them to be exactly all of them working, right? So they can only give you 7. The other 6 can be broken and the machine still works, right? Regardless, right? 7 or 14, right? And that's what makes that machine so awesome, right? Each core is powerful enough to do stuff. I mean, when you buy these PS3 games which are out in the market now, right? I suspect most of them can do 1 or 2, right? They're not using all the processing capability, right? But talking to some of the Sony folks, right? They have no idea what you can do with this stuff because they haven't been able to figure out how to get all of them to do interesting stuff, right? So they want to see how much each of the core can do, right? So when they want to do, I think three-person video conference, right? While you're playing a game, if you want to do three video conference with your players, you can still do that with one core, right? That one core is powerful enough to do that stuff, right? So they don't know what you can do with 7 cores, but it's out there, right? So the future programmer can develop that, right? So for example, what you can do is, if you play like Lord of the Rings movie kind of stuff, right? You can have each one of those characters have its own brain and act independently, right? It can live and do stuff independently, right? You can probably put like a few of them per core, right? So since there are 7 of them, you can actually have a game where 7 players or you're playing against 7 computers, right, in the same game, right? So that's much more of a compelling example to me than like PowerPoint doing spell check. I mean, spell check, you're typing at so slow a speed, right? You can do the spell checking really fast. But when you think about these, when you think about like these games, right? How many of you played any kind of games? Any kind of games other than like solitaire kind of thing, right? It's just I only play solitaire kind of games, so it doesn't count, right? But if you play these games where there are multiple actors and stuff, right? And the more cores essentially lets you assign a CPU to each one of them, so they don't have to share with you, right? So if you have one whose job is to kill you, it can make a decision all the time running on a CPU completely, right? If you build a game like that, it's going to be awesome. It'll defeat you in a jiffy, right? But other than that, you can do all the stuff. And that's what you're trying to do here. And so any game you develop for PS3 has to be massively multi-threaded, right? Because otherwise you're just wasting it. Why buy 7 cores if all you're going to use is 1 core, right? So one thread gives you 1 core. But if you want to build a real game on these systems, you got to use all the cores, right? Yes?
So if you do only have a single processor, but you have a multi-threaded process, does the processor just swap out the different threads so that it responds to all of this?
It's in the next slide, right? Hang on. So it does better resource sharing because they're all within a single process, right? And we'll see how you allocate it. Depending on how you allocate it, it can be really fast between switching, right? And the key, if you remember from before, is if I have to ask the kernel, things are slow, right? So if I ask the kernel, it's slow. If I can do it myself, it's faster. And that defines how I do that, right? And as we go to the future processor, it's not even a choice, right? If you buy a laptop or something these days, the dual core is so little, so the price differential is so little, right? In a few years, you're going to go for dual core and stuff. So if you buy a dual core machine and all you have is a single threaded process, you're not seeing the benefits of it, right? So if you buy a faster single core machine or a little slower dual core machine, unless you know how to thread them, you're not going to see the difference, right? For the most part, I mean. And some of the, so like I mentioned, if you want to do it within your application, things can be fast. But if you have to go to the kernel, things are slow, right? So that brings the notion of threads that the kernel knows and the threads that only the application, the user knows. Right? The user level threads are just that. I mean, it's a thing that you create within your own application. So within your application, you have to have something like a thread manager, right? You create a thread manager. Examples are POSIX threads, Win32 threads, or Java threads, right? And they run on the underlying machine, where the underlying machine does not know that you're threaded, right? You have to make sure that you create multiple threads in software and make them all run, right? And this is fast because since you don't talk to the kernel, you can switch them really fast, right? The challenge here is if one of these threads call the kernel and they begin to wait on this stuff, your thread manager will not get control, right? So it's good as long as you uncontrolled, you call the kernel. If one of the functions call the kernel, you're kind of stuck, right? Whereas in the kernel thread model, the kernel knows how many threads you have, and it can do the juggling. It can take somebody from running and so on and so forth, right? All the modern machines have threads, and the challenge is to map these things, right? So that's the 3 ways of mapping the threads, right? And I think that should answer your question, right? So many-to-one model assumes that you have one kernel thread that you are using software to manage this using, to give you many threads, right? From an application perspective, you see many threads, but from a kernel perspective, you see only one thread. So that this particular model does not really use the dual core or multi-core machines, but all it, so it gives you a sense that it just keeps switching between your threads, but not the underlying machine, right? A one-to-one model would assign one kernel thread per your application thread, right? So it only goes up to, so if you have a dual core machine, you can only have 2 one-to-one threads, right? Whereas many-to-many can have M to N. So you can have 4 user level threads and 2 kernel level threads, and you manage them, right? So it's kind of hybrid between these, the first two, right? And there's also more complication, which like one of them is a 2-level thread where you have some of the applications running on sharing a thread and some of them assigned to one. So in this case, there is one thread which is assigned to a single kernel level thread, and there are 4 application threads which are multiplexed on a single, on 3 kernel threads, right? So you kind of juggle these things, right? So these are different ways of assigning what you want from an application perspective to what you want from a kernel, from what you get from a kernel perspective, right? So I'll show the example, right? So can you, I don't know if you can see that. I think it doesn't like to focus in more, right? But you should have the handout with that program too, right? Right. So there is a few system calls that you need to worry about, right? If you look in the main function, right, the first instruction is the pthread init. So it creates the pthread module. It says pthread is the application level thread library, so initialize that, right? So on the next 2 sentences, you create thread. So essentially, when you say pthread create, you give it the attributes that you want to give the function. So in the first instructions, he is trying to start a thread to run add runner. In the second call, you call the subrunner, right? And you pass it a number which is sent as an argument to this program, right? So once you send these threads off, you go through this little I loop, right? And then you try to figure out what the sum is, and then you wait for the things to finish, right? So if you look inside the loop, both of them are the same, right? They spin so they add however many times you want them, or you subtract however many times you want them. So if I call this program with the value of 10, right? Add will keep adding 1 10 times, right? So you'll end up with 10. And subtract will subtract 10 times, so you'll end up with minus 10, right? So if both of them run on the same machine, you should come up with the answer of 0, right? Which is what you should get if you're running on a single processor, because first come in here, you only have one CPU, so one CPU should be assigned to the add runner, which will add the 10 times, right? And when it's finished, then you go to the next function. If this is a function, this is what will happen, right? You add it to 10, and then you subtract it to 10. So eventually, when you print the 0, right? So let's see how it works, right? So I'm on a multi-core machine. So on one of the machines that we're going to use for the course project, it's a dual core machine, right? So I compile it by doing gcc -g pthreads.c. Sorry, it's kind of going on the side, but it's minus L pthread, right? It compiles with the pthread libraries and so on, right? Now I have this program, so if I do 8 out of 10, you expect it to print 0, right? The program is so fast that one of them, went through. You can run this program to see which threads get to run and what happens, right? The answers can be anywhere between these two extremes because both of them are stomping on each other, both of them are overwriting whatever the previous one wrote, right? So every time you run this stuff, you should get a different. These machines are really fast that you have to give like a big number to see the difference, right? So if I give a big number, right, because of one of, there are actually two different threads running parallelly. So one of them is modifying the number, the other one is modifying. So if you go back to the right. The value sum is a global in both of them, right? That means it's in the code section, which is not in the thread. So since both of them are trying to modify it whichever way, right? Depending on who gets to write first, somebody succeeds, right? And this is basically the notion for the next module. But essentially, this is only happening because you have two CPUs, right? If you have one CPU, you're going through them in a sequential order, so you know what's happening. But since there are two CPUs, they're trampling on each other, and the next module we'll see how we can make this go and do stuff the way we want, right? But that's sort of the proof that these two things are running and trampling on each other, but they're running as two things, right? So they're both running in parallel, and that's so it's a fairly easy way to develop thread-based program, P-thread shared. In fact, most of your programs when you use Win32 and stuff already are multi-threaded, right? And because that's how you get, kind of interactive stuff, right? That's what I had actually. Was the example clear? The pthread library example? Yeah.
So what's the line do that says pthread join?
So there's the main program, right? It's always every process has at least one threaded, right? So when you create the add, it creates another thread, right? And you create stuff, right? It creates another thread, right? So they keep going, right? So there are a lot of things that we'll continue in the next class. One of the stuff is, when you do exit, right? When you exit from a program, right? In the case of before, when you exit, this didn't exist, right? You exit, you just go off, right? But here there are two other threads running, right? So you can only do a thread exit, right? So join basically says wait till all my children are done, right? Wait. So I created two other threads. I wait for all of them to come back, right? It's a good programming practice to say I'll wait till they all finish, right? Because otherwise it'll implicitly do that, because if you didn't do that, if you did exit here, then these two threads cannot just hang around wherever, right? And those bring up a lot of issues. So if you do exit here, right, what should happen, right? Because a thread is part of the same program, so anybody is equal, so they can all say the same thing, right? If you let this exit, that means everybody else would exit, because exit would kill the process, right? Remember, these are all inside a single process, right? See, if you exit a process from any thread, all the threads would have to die, right? Which may be annoying, but it could happen, right? So there are other questions you have to answer. So if you do a fork, right? Remember, fork makes a copy of all that you have into another process, right? Another copy of the process, right? So what would happen if you do a fork of this, this state? You should create a copy of this entire thing, right, with another process with 3 threads or whatever, right, with 3 threads and doing this stuff kind of thing, right? And so the thread join is a nice way to say, I know what's happening, so I want to wait for the whole thing to finish kind of thing, right? For the most part, threads are fairly easy to use. I mean, there are a couple of calls you need to figure out, and then off you go, right? The cases where you fail is things like how do you do exit, how do you do fork, and what happens when you get an interrupt, right? And what happens when you, so both of them have the same stuff, right? So if you do a read here from the terminal and you do a read here from the terminal, what should they get, right? If they're both running simultaneously, then it's undefined. I mean, you get to be a bizarre program. And that's one of the reasons why people don't like thread programs, right? Because you have to be aware it's not just one, but there's many, right? So you could potentially be waiting on the mouse and the keyboard, what she was asking in a previous lecture, because this is waiting for one, this is waiting for another one, right? You could potentially be waiting for something here while this is progressing. You can be talking to the keyboard here while this is running, right? For the most part, it works, but when you have bugs, you create bizarre conditions, right? You create bizarre conditions because you have to think about not just one, but you have to see what this whole program is doing. So you have to say, this is what should be happening. Like, this thread is doing this thread is doing this thread is doing this thread is doing this, and my thread is causing problems, right? But since they're all independent, if one of them makes more, moves ahead, it's kind of hard to debug, right? The other weird things with the threaded program is, depending on the number of processors you have, you'll get different results, right? If you take the same program that we talked about and run it on a single processor machine, you'll get one set of results. Take it to a dual processor machine, you get another set of results. You take it to a quad core machine, you may get different set of results, right? So debugging them is really annoying because you have to ask how many processors do you have and what do they do, right? And you may actually face it for your homework project too. Like this is a dual core, it may not be as bad because you have enough CPU to go around, right? And we'll look into all of that on Monday. Essentially, what threads add, right? So they're a pain, but if you're like, for example, the PS3 game developer, right? You don't use threads. What's the point of PS? You probably stay with PS2 kind of thing. So you're forced to deal with these things. Right? We'll send you on next class.